Hello, everyone. It's great to be here with you today. First of all, thank you very much for the organizing committee for inviting me for this keynote speech. I really appreciate that. It could have been better to be in person with you today, but we learned how to communicate in different environments, virtually, hybrid, or in person in these current circumstances. Today, I'm going to talk about a thing which is very, very close to my heart. It is robotics. And let me start by saying robotics is a job creator, not a job taker. When I started my journey in 1998, most of you in the audience might not remember that well, that time. I'm hoping most of you are very young. Robotics was not that popular. There were things happening over there, but when you look at over the years, the progress that has been made in robotics, AI, data analytics is tremendous. The recent pandemic has created a different mindset about using technologies. In the Australian context, I'm sure you might have heard about these critical technologies, in which robotics is a major part. And we are currently thinking about an Australian robotics strategy. So all things are happening for a reason. Robotics can do amazing things. In the past, people used to say it is more suitable for 3Ds, dirty, dull, and dangerous. But it's going beyond now. It's going beyond those conventional robotics, and it becomes a vertical it is becoming horizontal, meaning that the robotics can have applications in many verticals. For example, it can be defense, it can be agriculture, it can be infrastructure, or it can be healthcare. So many opportunities and so many ways that the robotics technology can help people to do things better. So it is fascinating to talk about this today, mostly trying to capture robotics in disaster management side. I'm going to talk more towards that, but it may not be exactly applying robotics into disaster management, but you will see the advancement that we do in my institute, how that could be easily transformed into the applications where it can be used in robotics for disaster management. So if you look at this, it's already happening. Robotics technologies in various formats, it has been applied in order to manage in disaster situations. If you look from the top, UAVs, drones, which can navigate in difficult terrains because it is going through air, and flood environments because it is again going through air. And there are many applications to that, including delivery of medicine or essential items, or do reconnaissance jobs. So go have a look and give that information back to the responders. There could be ambitious amphibious robots where the robot can navigate in water as well as on the ground, which is a really useful tool, especially when it is flooding. There are AUVs, autonomous underwater vehicles, where especially for applications of flooding or in sea or rivers, in disaster situations, that can be used there. There is another type of robotics where we call biologically inspired robotics. That is, you look at how the biological species work, how they perform different tasks, study that, and develop robotics based on that studies. So those are, in this one that you can see over there, is a snake-looking robot which can climb on branches and race. There are ground vehicles, the one that you can see at the bottom, very rugged ones, so that you can even drop these robots from 2-3 meters and it still will be operational. And you can use combination of all the technologies in order to gather information, in order to help the victims. So robotics can have many applications there. But today, what I'm going to talk about is how the work that we are doing currently, which is in the areas of robotics for infrastructure maintenance and inspection, how can we use that technology maybe in disasters. So I'm going to talk about few of the pilot studies or examples, research areas that we work to give some understanding about how this robotics is evolving, what are the state-of-the-art robotics technologies which has been used to inspect and maybe repair of different infrastructures. So one of them is critical water pipes, those are underground pipes, or underground sewer network, or bridge inspections above ground, or the pylon inspections. So when you look at the critical water structure, it is huge in any country. When you look at UK, US, and Australia alone, it is worth over $500 billion. And if you look at Australia alone, over 140,000 kilometers of underground pipes to deliver water from one place to the other. But as customers, what we expect is when we open the tap, we need to have water. What we haven't thought much is about how, when, and where the pipes can burst, because those pipes could be buried 100 years ago. This situation becomes much more worse when it is happening in an area where you have other critical infrastructure. For example, imagine a high-pressure water pipe bursting in middle of Sydney or middle of Melbourne. That has social, economic, and financial impacts. You might not know that in Australia alone, there are approximately around 700 main breaks per year. These main breaks are bigger pipes, high pressure pipes. It is not a small number. Then how can we inspect that? You can't dig everywhere and expose the pipe and start inspecting. You need to have some other mechanisms. One of the ways of doing that is to insert a robotic system which goes inside the pipes and then estimate how much corrosion happens, or in other words, estimate how much is the remaining wall thickness of those pipes. When in the context of Sydney or New South Wales, most of the water pipes are cement-lined cast iron. It has a certain property of failure. It fails by destroying itself. In other words, it is brittle. The steel pipes don't have the same failure mechanism, but cast iron is going to be brittle. It will be burst open. So the corrosion which can happen because of the corrosive soil, or internal corrosion can happen because of the presence of moisture. Both can corrode, but because those are cement lined, the internal corrosion is less. Then it's a matter of coming up with sensing technologies in order to figure out how much is the remaining wall thickness, and also to figure out how these sensors can be deployed in pipes. The one that you can see on the right-hand side are two robots, which is designed by our colleagues in the Robotics Institute, which has a cocoon of sensors around it that is based on the pulse eddy current. And then it has cameras in order to three-dimensionally reconstruct. And then once you deploy it inside a pipe, it takes measurements around the pipe. And if you cut open the pipe and make it a rectangle looking or flattening, you will see a picture like this, which has a color coding according to the remaining wall thickness. These I have values, so this can be used, and these are being used in order to estimate what is the remaining life of this pipe. But visually, once we are deploying the robot, you can see it with these colors so that you can straight away identify whether this pipe needs to be replaced or not. Deployment is not that easy. You need to have opening, and then you need to have a tether mechanism. You don't want to send a pipe robot without tethers. In case if it goes wrong, you need to be able to pull it back. Otherwise, you won't have water for a while. And you don't want to have any batteries because, to obvious reason, you don't want to contaminate. So, different requirements from different utilities. As you can imagine, the water pipes are bigger and small. It has a huge range of water pipe. The water pipe which is coming to your house is small, and then go to the street level is bigger. Suburb level is even bigger. So it has a range of diameter. How could you design something in order to cater for that? There can be bends. 90 degree or 45 degrees common. So how could you still manage that bends? So there are many challenges. And the other challenge is, in most cases, the team that RI, Robotics Institute, how they are working at the moment is, when there is a pipe burst happens, Sydney Water call in that team and that at UTS. So that team goes there and take that as an opportunity to deploy the robot from that burst point, because the pipe is shut down already, and then go both sides and estimate what is the remaining wall thickness. They don't want to see any other burst happening next to that site. That's one. The other aspect is called planned maintenance, where the water utilities will shut down the main for a particular time, and then crew will deploy this robot during that time and assess the condition of that. The third type is, in the both two types that I mentioned, the main need to be shut down because those are high pressure. It's very hard to work with that. The third type the team is working on is what we call hot insertion type robots. They won't use a water hydrant and with the mechanism, so that the robot is going to be inserted while the high pressure water pipe is in operation. So it's very challenging, but the team is working on that. So I'm going to show a video here.
It's called the R2-T2 Rapid Response Robot, being used right under our homes across Sydney. A new solution to an old problem, leaking water mains, wasting precious water at a time of drought.
One of the challenges in a drought is that with the drying surface underground, it can crack pipes.
Sydney has around 175 major leaks every year, losing 156 million litres per day. That's more than 60 Olympic swimming pools. Now cracks and corrosion can be detected without digging. Today we were given an exclusive first look at the high-tech solution.
Really exciting. There's a whole host of possibilities in terms of what the technology can offer.
The R2-T2 is the first of its kind in the world, and now Sydney Water is hoping to create a fleet of robots to cover its entire network, and other parts of the country are now interested in the technology. Created by engineers at UTS, technicians can watch in real time using virtual reality headsets while the robot surveys the pipe.
And to have this technology now at the front foot of ensuring that our water supply extends as long as it can is really important.
The cracks can now be fixed with quick drying epoxy spray coating. No need to replace the entire pipe.
One reference to that was the drought, but this video was recorded sometimes back when we had the drought. Now, most of you know that we are flooded with rain. So it's a different scenario, but the problem itself is still there. The other aspect that I wanted to talk about is the other type of infrastructure, which is sewers or wastewater pipes. Again, any city has a network of infrastructures. The difference is they may not be metallic. They may not be cast iron cement line pipes. Most of them that you see in major cities are huge, and they are not really round shape. There could be many different shapes. So the challenges are different, and most of them are cement or concrete tunnels, reinforced or not reinforced with metals. Australia alone, we have around 120,000 kilometers of sewer pipes. It's long, but again, as you can imagine, the sewer pipes going from your home is small. When it goes to the street level, it's bigger. When it goes to the suburb level, it's even bigger. And even in the cities, this could be huge, so that people use boats to go in there and look at and do the inspection. This picture is from the web. This was one of the ways of human inspection. This was in Bangladesh. This poor person had to go down in this sewer in order to remove that block. of the sewer. It's very dangerous. When you remove the block, all the water is going to be sucked and even the person can be taken away. So there have been reported human life losses due to not using or not affordability to use tools, the right tools. In Australia, you don't see this. However, you might be surprised to know that in some areas of sewers, people need to still travel through with some equipment on their hands, have a visual inspection, take core samples, take to the labs and analyze them in order to see whether corrosion has or this sewer pipe has been corroded or deteriorated. This is again a multi-billion-dollar problem all over the world. Currently, almost all of the managing utilities are either rely on people going into the sewers, which is very dangerous, or using camera-based techniques like CCTV. As you can imagine, cameras can only tell what is happening on the surface. So then how to avoid failures? This will give you a brief rundown of what a sewer looks like. This is one of our guys going inside the sewer from a manhole. Can you remember? Think about this is a very small manhole and he's capturing the data while he goes down because there's a GoPro mounted. And this is supposed to be a reasonably good sewer. So goes down, have a look. What we are dealing with is something like this. There are other pipes connecting, so water can fall from there. There are cockroaches and other species there. There are areas which are corroded. There are areas where the water comes through other pipes and there are turbulences. One good thing is the sewer is not 100% full. Bad thing is there are so many things in the sewer. The things that you flush and the things that unintentionally or intentionally put into the sewers. So everything is there. Just to give a brief idea about how the sewer corrosion happens, I use the word corrosion. This is not metallic corrosion, this is concrete corrosion. So when we flush things, there are sulfates in those waste, and then in anaerobic conditions, this converts into hydrogen sulfide. This is dissolved water. And then when turbulence happens, it becomes gaseous hydrogen sulfide. And there are bacteria living on the surface who convert that or consume that hydrogen sulfide and convert into sulfuric acid. Sulfuric acid attacks the concrete, making it brittle. That is called corrosion. So when you have the sewer, you have a corroded layer or a brittle layer, and then reinforcement bars, and then the good concrete. So if you send a CCTV, you will see only surface. You don't know how much corrosion or the brittle part of the concrete is. Without knowing that, it is difficult to do rehabilitation because you don't know what you are looking at. So the project that we are working on is to identify what is the good concrete left, what is the level or what is the depth of good concrete left. We have developed this robot, which is floating because sewers you can't stop normally. And there are so many things on sewer water, including human hair and tissues, which can easily clog the wheel robot. So this particular robot was designed in such a way that it floats with the gravity. At the same time, it can expand its arms, which are having sensors like the ground penetrating radar or pulse eddy current, in order to scan of what is happening underneath the surface. One other difficulty is, you may remember, people need to go through that manhole, which is around 450 millimeter diameter, so small. This robot needs to fit through that. That's how you deploy. And then expand into different sizes. For example, this particular robot can expand up to 1.5 meters diameter. And then you need to have a good visualization technique. This needs to be stable. And there could be things, silt and other things in the pipe, so that it has some other forces which can be challenging to overcome. At the same time, it needs to be tethered. Otherwise, it's very hard to take it back if something goes wrong. So what we proposed is manhole to manhole deployment. It could be around 300 meters, up to 300 meters in between two manholes. So deploy from one manhole, it goes to the other manhole, you retrieve from there rather than having to pull it back. So this is what you see once you do that scanning. So it will three-dimensionally reconstruct what the tunnel is or the pipe is. And then it will figure out whether there are corrosion and what is the depth of that. You can overlay that on this. Then after, it will figure out where the reinforcement bars are with respect to the surface. And then it is integrated into this visualization. So you have all the information that you required in order to make renewal decisions. And this is one of the deployments. It is logistically significant. You need to have tripods. You need to have trained people in order to deploy it through that manhole. And then you have a remote control station in order to visualize and see what is going on with that. This is another video that will give you some background about this sewer robotics.
Sewers is an integral part of any society. This issue is an international multi-billion-dollar problem for the water utilities around the world. Today, we walk the sewers and make decisions based on judgments rather than evidence. This is a great innovation that would be useful to any utility around the world.
Sewers can obviously carry the wastewater from our homes and our industries, have operational, environmental and asset concerns, and we're looking to address that by finding new ways of doing things with our partners at UTS.
This project has two main challenges. One is in sensing, the other one is in the deployment. The sensing challenge is handled through a multi-sensor data fusion approach, the sensory data coming from different sources, and combine it through state-of-the-art machine learning technologies. So this will provide a great insight into the whole pipe structure, including visual, structural, and subsurface information. The deployment challenge was handled by carefully designing a robotic system which can go through a 600 millimeter diameter manhole and yet expanding into 0.5 meters or 1.5 meter diameter pipes. Therefore, this is the world's first robotic system which packaged sensing, artificial intelligence, and mechanical designs to build the most comprehensive sewer condition assessment tool.
Finding new and better ways of working through innovative technologies is really important to us at Sydney Water. We spend around $40 million a year actually rehabilitating our sewers and actually making them work for our community and our customers. We have found that working with UTS is identifying new technology in robotics, in sensors, that actually allows us to do it cheaper and more efficiently. One of the most important things is actually catching any damage or area repair early. If we can do that, we can reduce the cost of servicing by 8 to 10 times compared to when it is actually fully damaged and when we can inspect it.
Currently we're working on a very innovative program with UTS in a collaborative research project to develop a sewer robot that will actually go through and do this work for us. This will save us time, money, and obviously take the safety component of working in confined spaces in our sewer spaces.
One of the most important things for us is how we operationalise this new innovation, turning it from a pilot or a lab scale study into an operationalised output. And we are working really closely with our delivery partners about how we can actually get robotics and sensors on the ground in our infrastructure to actually deliver the benefits to our communities and our services every day.
This is another video of a real deployment. So you get some idea about noise level, the environment. Thing that I can't show you in person, but this is how the water is flowing at a faster rate with turbulence, and you have vent in the pipeline. So just to show real deployment. The one that you can see out there is the robot, and this is the feather. So this is taken from video screen, the camera which is mounted on the operator. The next thing that I want to talk about is bridge inspection. So it is above ground. Challenges are different. One famous bridge is Harbour Bridge. So we have several robots. Our colleagues have developed several robots which can inspect for corrosion and do some repairs. So the challenges are every 2 years' time, people are deployed for inspecting, starting from one side of the harbour bridge and goes to the other side. It takes roughly 2 years, and then they go to start again. Not only inspection and grid blasting. The grid blasting component is tricky and hazardous because the back pressure can develop back pain, and it can have lead. So it is not a great environment for humans. Therefore, the RMS, Road and Maritime Services, has started this negotiating a project with the colleagues of mine and to develop this robotic system which can scan the outside of the arches and then identify areas where paint need to be grid blasted, removed because it's corroded, and then does that grid blasting by a robotic system. So somebody can be away in a remote control station. The robot is doing that work.
At 81, the Sydney Harbour Bridge does look good for her age, but requires constant maintenance. It is, as you'd imagine, an enormous task. The bridge was built using 53,000 tonnes of steel. The surface area to be repainted is about the same as 60 sports pitches. 2 robots called Sandy and Rosie have been brought in to do some of the more dangerous and awkward jobs in those hard-to-reach places. Their mechanical arms are 2 meters long and have half a dozen joints to give them the dexterity they need to blast away old paint and rust from one of Australia's most recognisable landmarks. The robots use sensors and cameras to navigate unfamiliar terrain. The technology is the result of a 6-year collaboration between the University of Technology Sydney and the New South Wales State Government. It wanted ways to protect workers from lead paint and other hazards. The challenge for researchers was to build a machine that could work in such difficult conditions. The Harbour Bridge was opened in March 1932. It was an engineering wonder then and still is today. It's held together by more than 6 million rivets and is a vital cog in Sydney's overstretched transport network.
It's an unknown and very complicated and cluttered environment. So our researchers had to go back to square one and rethink about how the robot would figure out what to do. So it actually builds its own map. It takes pictures and three-dimensional data, maps all that together, and then uses that as a three-dimensional image of the structure, and then works out the best way to blast it and gets on with the job.
This is the world's largest steel arch bridge. Its total length is 1,149 metres. Repainting the grand old coat hanger that spans Sydney Harbour is a never-ending task. Robots Rosie and Sandy, which each weigh 25 kilograms, have become full-time members of the maintenance operation. They're not replacing their living, breathing human colleagues, but have become an important and intelligent part of the team that's keeping this grand old lady looking good in old age. Phil Mercer, BBC News, on Sydney Harbour.
The next that I want to talk about is, this is the previous video that you have seen is outside of the arches. So it is external inspection. The next thing that they had was internal inspection, because if you look at those arches, those are hollow. Those are not solid structures. Therefore, somebody needs to creep in there. The manholes are very small, and going from one section to the other. Again, it's dangerous, very confined space, and depending on the weather, they might not even do it. So that difficulties was addressed by having another robotic system, because the one that you have seen is a bit bulky. You need a different type of robot where it can crawl inside and then identify the areas, map the areas where corrosion is present, and then send that information back.
A climbing robot designed to inspect hidden passages inside the arches. Engineers at the University of Technology in Sydney have teamed up with Roads and Maritime Services to develop the machine, which navigates around the pitch-black tunnels, checking the condition of the bridge.
The Harbour Bridge has her secrets, a vast network of hidden passageways. It's the first time this section has been opened in 5 years. The paintwork dates back to 1932. This robot's designed to get into small spaces and climb around the arches, checking for defects.
It's safer, definitely. It's better to send a machine in a confined space than myself, because if something happened to me, I would be blocked.
High above the road, there are internal tunnels with steep drop-offs. There's no room for a stretcher, and small openings every 6 metres would make a rescue difficult, if not impossible.
There's risk of asphyxiation, air quality is an issue inside the arch. These days we prefer to send robots in to do the dangerous jobs.
The robot navigates using a 3D sensor, creating a map of the space and giving engineers crucial detail about what needs fixing.
There are more than 7 kilometres of these narrow passageways along the arches of the bridge, and the next stage of this project will see a robot clean and paint the area at the same time.
The next robot will use lasers to vaporise rust, have a vacuum to remove it, and a machine attached to paint safely without the need for workers to delve inside.
We can see this on other structures, like transmission towers and ship hulls, nuclear reactors. So other places where you don't want to send people, it's too difficult to access.
Robots won an International Technology Award in Sri Lanka and a Work Safety Prize back home. It's hoped the next version, complete with lasers, will be ready in 3 years' time. Nicole Chettle, ABC News.
The next robot, as it was mentioned towards the end of that video, is about taking a payload so that it can remove those paints inside the arches. Because once it is inspected, again, if some human has to go there, it's low risk because you know exactly where it is, but still it is risky. So the RMS wanted a system which can remove that paint based on a laser and then repainting. So this robot was designed to carry a larger payload and then to do that task. So the one that you see here is the sensing mechanism in order to identify what is around it and map that environment. And then this is the robotic arm, which can take that laser-based paint removal. And as you can see, that is tethered as well. And it can go through the very small manholes from one section to the other. So that's a requirement. So how it goes is by pressing its legs against those walls and moving forward. So that's another robotic system which is used for inspection of these bridges like structures. So the next one I want to show you is about the pylons. The conditions are different because pylons have marine growth underwater. How it is removed at the moment is people dive and then they have a water blasting mechanism. So they dive and then start water blasting, high pressure water blasting. So all the marine growth is going to be removed, but it's going to go into that person. It's not a very good experience. So again, RMS was working with our colleagues in the institute in order to come up with the underwater robotic system, which can go and hug into the structure, do the mapping, identify which areas they have enormous marine growth, point the high pressure water gun, and then remove it. After removing, have a map again to see whether it is intact. So this video explains that.
Routine inspection and maintenance of underwater structures, such as bridges and wharf piles, are important to ensure the integrity and prolong the lifespan of the structures. In order to assess the condition of a pile, the covering crustaceans and other marine or aquatic growth need to be removed, either by high-pressure water cleaning or hand scraping. At current, this operation is primarily conducted by human divers, which exposes them to very hazardous work conditions, including poor visibility, strong water currents, high-pressure water jet, and working in awkward poses. There is an urgent need for innovative solutions to address these significant work, health and safety issues, and to improve the efficiency of condition assessment and maintenance of underwater structures. Researchers and engineers from the Centre for Autonomous Systems at the University of Technology, Sydney, and the Roads and Maritime Services of New South Wales have worked together to develop submersible pile inspection robots, aka SPEAR, for autonomous cleaning and inspection of underwater structures. The SPEAR consists of claw arms used for docking rigidly onto a pile, an arm for surface cleaning using a high-pressure water jet, and an assortment of cameras and sensors for perception and environmental and operational awareness. Once navigated to a pile, the SPEAR will conduct the operations autonomously, including simultaneous localization and mapping, identifying surfaces and marine growth, navigating and docking onto different positions around the pile, and planning and executing a water jet trajectory to remove the marine growth. After cleaning, the SPEAR collects high-definition images around the pile that are geo-referenced with a 3D map constructed of the pile and can be used by bridge inspectors for condition assessment. A simple user interface allows bridge maintenance workers to monitor the operation and view live video feeds from the safety of a boat. The SPEAR is applicable to other applications, such as autonomously cleaning of ship hulls, offshore structures, and underwater pipelines.
So that is some of the work that we do in terms of infrastructure inspection. As you can imagine, or as you have seen, those are not particularly targeted at search and rescue scenarios. But as you can also appreciate, most of these technologies can be used in disaster situations in order to inspect pipelines, sewers, integrity of the other structures such as bridges or towers. There are a few challenges over there. One of them is the sensing challenge. So depending on the task, what are the required sensors in order to achieve that task? For example, what information is usually required? In these particular cases, it is about either visual inspection by using cameras, laser-based sensors to map the environment, ground penetrating radars in order to penetrate through a structure and tell what is happening inside the surface, under the surface. Pulse eddy current sensors, which can tell what is happening with the metallic structures. There are some other integral sensors, inertial measurement units, GPS, global positioning systems, and many other sensors in order to achieve the location, the mapping, analyzing the structural integrities, so on and so forth. So in this particular conference, which is the target is more on disaster management. So some of these technologies may be useful after a disaster to check the integrity of different structures. At the same time, the work that we are doing in the areas of drones, underwater vehicles, and ground vehicles, and how they can communicate in order to maximize the information, identifying victims based on, let's say, thermal cameras or audio signals. This can be integrated into such systems so that the responders have a much better idea of what is happening, where are the victims, so on and so forth.